take a look at the r of x equals 1 over x squared. And everything that's being asked here, the domain of this function, the intercepts, and finding the r of negative x and the negative r of x are all things you should be able to do by now. So why don't you pause your video and give those a try. So let's see what we have so far. For the domain, we know that the denominator cannot equal 0, so x cannot equal 0. In interval notation then, negative infinity to 0, union 0 to infinity. For my intercepts, I first found my x-intercept and let y equal 0. But I can see that this is never going to equal 0 because the numerator is 1, and 1 does not equal 0. So there are no x-intercepts. For the y-intercept, we let x equal 0. When we let x equal 0, we see we have 0 in the denominator, which is of course not permitted. So there are no y-intercepts. So you found the r of negative x and the negative r of x, and we notice that the r of negative x equals the r of x. That tells me that this is an even function because the r of x was exactly the same as the r of negative x. So let's graph this function. I've given you some values of x to substitute in. So let's start with x equals 1. We're going to find the r of 1. Which is of course equal to 1. Why don't you find these other values? Were these the first 4 values you found? I hope so. Let's just look at x equals a half to be sure you're on the right track. If you were finding the r of 1/2, this is equal to 1 over 1/2 all squared, which is the same as 1 divided by a half squared is a quarter. And of course, when we're dividing, we multiply by the reciprocal. This was equal to 4. I hope you were able to evaluate each of those without a calculator, of course. Now, if you look at these values of x that I have here, they're getting smaller and smaller and smaller, but not negative. We started at x equals 1 and then went to 1/2 and then 1/10 and then 1/1000. So we were approaching 0 from the right side on the number line. And as we did that, the r of x or y was getting bigger and bigger and bigger. It was getting closer and closer to infinity. So we say in calculus then that the limit of the function as x approaches 0 is equal to infinity. We write that the limit of our function as x approaches 0 equals infinity. Find the values for y or the r of x for those negative values of x. Do you notice that these values of x are also getting closer and closer to 0? This time we're approaching from the left side on the number line. And as x gets closer to 0, again, the r of x gets closer and closer to infinity. So we can say that the limit of our function as x approaches 0 is again equal to infinity. I've graphed these ordered pairs here, and you can see that from the left and from the right, x is getting closer and closer to 0, and y is getting closer and closer to positive infinity. But what's happening over here? Why don't you find these values of y given these values of x? So notice that this time our values of x are getting bigger and bigger. They're approaching infinity. But as x approaches positive infinity, we see that the r of x is getting closer and closer to 0. We say that the limit of our function as x approaches infinity equals 0. In the next box, x is getting closer and closer to negative infinity. And r of x again is getting closer and closer to 0. So the limit of our function as x approaches negative infinity is equal to 0. Let's add this to our graph. So what we end up having are two asymptotes. We have this vertical asymptote where x equals 0, because of course we said the limit of our function as x approaches 0 is equal to positive infinity. This gave us our vertical asymptote at x equals 0. We also have an asymptote here, a horizontal asymptote at y equals 0. The limit when our function had x approaching infinity, both positive and negative infinity, was equal to 0. This gave us our horizontal asymptote at y equals 0. We're going to look at a method for finding asymptotes, both horizontal, vertical, and also oblique asymptotes in another lecture.